Hello and welcome to this lecture. We will study what's called singular value decomposition in this lecture. In the previous lecture, we saw definitions of singular values of an operator of a linear map and singular vectors of a linear map, right singular vectors and left singular vectors. And there was this very interesting relationship between the map and its right singular vectors and its left singular vectors and the singular value, right. So that was something we did not prove in the previous lecture. We just saw it, and we will prove that in this lecture. Okay, so it's mainly a proof of what's called singular value decomposition. This lecture. Okay, I'll skip the recap. We saw it in the previous lecture. The main idea is that this definition of singular values and vectors, which is basically eigenvalues and eigenvectors of t star t. Okay, singular values and singular vectors of t are basically eigenvalues, eigenvectors of t star t and t star also, right. The left singular value is that of t star. Okay, a few preliminaries before we formally describe singular value decomposition. I will describe it in two ways. One with respect to matrices. It's very popular to study singular value decomposition purely as a matrix sort of result. We will also see an operator sort of version, and finally we will prove it in the operator version. That's why we will prove it. Okay. So a few basic ideas. Many of these ideas you must already know, but I am just trying to reinforce them because these will show up in the definition, and you need not be surprised when you see it in the definition. First is that of a unitary matrix. We have already seen this before. We have seen isometries, and we saw that unitary matrices represent isometries, unitary operators, right. These are isometries. The basic definition is an n cross n matrix V is said to be unitary if its columns are orthonormal. Okay. So another way of writing it is V star must be the same as V star V, and that should be equal to the identity matrix I. Okay. So V star is basically conjugate transpose. From here you also see that V star is V inverse, right. So that's also something that's important. Okay. Inverse is the same as conjugate transpose, right. This V star is conjugate transpose and inverse is the same as that. The product is 1. So this is a unitary matrices, and unitary matrices, like I said, represent isometries. So isometries are pretty much how do I say it? They don't do much in some sense, right. So they don't change your landscape in anything in a significant way, right. They take they preserve norms, they preserve inner products. It's almost like a rotation. So you're not changing much when you do an isometry in some sense. It's sort of like an equal thing. Okay, so that's one way of thinking about it. Another notion we will need is this notion of rectangular diagonal matrices. We know what square diagonal matrices are, right. So we know the main diagonal. It's easy to talk of diagonals with a square matrix, but with rectangular matrices, how do you describe diagonals? It's not very different. So even if you have a rectangular matrix, I'm simply drawing a rectangular matrix here. This would be the main diagonal. Okay, so this is the main diagonal. Okay, basically 1, 1, 2, 2, so on. So even if you have a tall matrix like this, the definition of diagonal is the same. Okay, so if you have m cross n, this is diagonal. If you have m cross n, m being larger also, that's diagonal. Okay, so this is the main diagonal. 1, 1, 2, 2 extra. Okay, so when do I say a rectangular matrix is a diagonal matrix? It's only if the non-zero values, if they show up only on the diagonal, then the rectangular matrix is also called a diagonal matrix. Okay, so this is a convention that we will use. Both these unitary matrices and such rectangular diagonal matrices will show up in the description of the singular value decomposition. Okay, so that's why we need this. So these are preliminaries. Hopefully it's clear. Okay, so here is the singular value decomposition in terms of matrices. Okay, so this is a very popular way in which it's described anywhere that you read it. So I think it's good to see it with matrices first, and then we'll go to the operator view, and then we'll prove it. Okay, so if you have an m cross n matrix, we know that there are singular values for this, which is the eigenvalues of a star a or a star, right. So both of these, we know the non-zero eigenvalues are the same, and the zero eigenvalues will differ depending on the rank and size and all that. Okay. Then you have right singular vectors. These are the orthonormal eigenvectors of a star a. Okay. Now, I mean, there's some ambiguity about uniqueness here. I mean, so orthonormal eigenvectors, when you have repeating eigenvalues, it's not unique, isn't it? So you can have multiple types of orthonormal eigenvectors, and so right singular vectors also are defined in that fashion. You can have different sets of right singular vectors. Okay. Same thing with left singular vectors. These are orthonormal eigenvectors of a star. Okay. Okay, so A star A and A star. Okay, so since M can be different from N, these are all different things in some sense. Okay, yeah, that's the setup, and the SVD is basically a decomposition of A into the product of three matrices. Okay, so SVD, singular value decomposition, basically states that there exists an M cross M unitary matrix U, an N cross N unitary matrix V, and an M cross N diagonal matrix D, such that A can be decomposed or written as a product of three matrices and all three, right? So U, D, V star. Okay, so you know V star is the conjugate transpose or the inverse of V, and then you have D, and then you have U. Okay, so it's a product of these three matrices. So now, if V is unitary, V star is also unitary, right? Okay, V star is also unitary. So when you write A as the product of these three matrices, and when you apply, so when you do U, so when you do AV, it's, or maybe AX, it's U D V star X. Okay, so when you apply A on X, or X is input to this transform A, and then you do AX to get the output, you can equivalently do it first by multiplying with V. Okay, and this guy is just it doesn't change X that much, it's just a unitary transform. Okay, so at this point, okay, the vector that you would have, right, V star X is sort of a change of basis to columns of V. Okay, so that's what this V star X is going to do. And then you do D times V star X, and D is diagonal, right? So it's just going to be scaling of the coordinates at this point, and then you multiply by U. And what is multiplication by U again? It's again a change of basis, isn't it? Change of basis to so you've gone to a different basis here, so then you multiply by U. So remember, this has gone to from Fn to Fm, right? So after multiplication by D, it's only a M length vector, right? And that M length vector, I don't know, it gets multiplied by U. Now there is a further change of basis by this unitary matrix U. And what does unitary matrix do? Nothing much, right? So it's sort of like, I shouldn't say nothing much, be careful here. So it's just sort of rotates or something like that. It doesn't change the metric, the norm doesn't change. So it just gets multiplied by that. So any A, however complicated it may be, always decomposes like this: unitary multiplied by diagonal multiplied by unitary. Okay, so that's the idea. So once you see that, you'll see how interestingly one can work with this. So it's very, very promising, and it has so many different applications, etc. But this is the main SVD result. Okay, so any matrix A can be written as a product of U, D, V star, where U and V are unitary of suitable dimensions, M cross M and N cross N, and D is diagonal. Okay, diagonal, rectangular diagonal matrix, M cross M. Okay, so that's the interesting part. So once again, what are these U, V and D? U, the columns are left singular vectors. For V, the columns are the right singular vectors, and for D, it has the singular values of A on the main diagonal. Okay, so this also is an important result. Okay, so you have the existence of these three, and how do you find these three? D simply needs the singular values, V needs the right singular vectors, and U needs the left singular vectors. That's it. Okay, so simple enough in a way to look at. Okay, and you get the answer you want. Okay, so this is SVD in terms of matrices. You look up any book or website or something. This is how SVD is described, and the simple. I mean, we will see more detailed applications later on, and we'll see this kind of decomposition is very, very, very powerful. So see, if you have a self-adjoint matrix or a self-adjoint operator A, then you can write it as VD V star. Okay, so that's really, really very powerful, and we saw so many different applications of that. Now here the U has changed, right? So in fact, this result you can also use it for a square matrix. Supposing A is a n cross n matrix, and maybe it's not self-adjoint, then what happens? You can write A as UDV star. It's not VDV star, it's UDV star, and U is still unitary. Okay, so it's not by much. except that you view it in a different axis, which is all orthonormal, the operator becomes diagonal. Okay, so that's the powerful statement here. Okay, so this is SVD in terms of matrices, and let's see a quick example to firm up matters here. So this is an example we've seen before. Okay, this 2 by 3 matrix 1, 2, 3, 4, 5, 6. We computed the singular values, we computed the right singular vectors, left singular vectors, and then using this you can check that A will work out as this product. Okay, so we have seen this before. This is how A will work out to be. Okay, so you can check this again. Hopefully this is correct. So I have not made a mistake here. So you will get A to be the product of these three things. Okay, so notice something that's very interesting. If I change basis, right? So this A was in standard basis. Let's say standard basis for F3 and standard basis for R3 and standard basis for R2. Okay, so it's in the standard basis. Now if I change basis of R3 to E1, E2, E3, okay, remember this is this matrix is E1, E2, E3 star, right? So conjugate transpose. So E1 comes on the first row, E2 comes on the second row, E3 comes on the third row, right? So this is that. Okay, so this is like the inverse of that. So it takes from standard basis. So here the coordinates will be E1, E2, E3 basis. Okay, is that okay? So then you get an answer which is in F1, F2 basis, isn't it? So if you shift the basis to F1, F2, here the answer is in F1, F2 basis. So here you go back to standard basis. Okay, so in terms of coordinates, this is how you can think about it. You have input coming in standard basis. When you multiply by this unitary matrix V star, you go to the basis E1, E2, E3, the coordinates are in that basis, and you do the your linear map, right? So it's just a scaling at this point. You will get the coordinates in F1, F2 basis, and then from F1, F2 basis you go back to the standard basis by multiplying by U. Okay, so this is a description. So if you change basis to R3 and R2 and look for the matrix of A in that basis, then you simply get a diagonal matrix. Okay, so both these are equivalent, as A being written as this and this are equivalent, right? So A being written as U D V star, and A in the basis of columns of U for our Fm, and then the columns of V for Fn, it being just diagonal, both of these are exactly equivalent. Okay, so that's sort of an example which sort of illustrates how SVD works in practice. So now this can work for even an arbitrary matrix. For any matrix you want, you find the singular values, find the right singular vectors, left singular vectors, you have this decomposition, you go to the orthonormal basis dictated by the singular vectors, then your linear map A becomes diagonal. Okay, so that's the power of this SVD. Okay, so now we'll do a restatement in terms of operators. We saw the example before, it's sort of motivated by that. Let's say you have T being V to W being a linear map, then you have a basis for V, basis for W, and then you can think of a matrix for T in this basis. So what is the matrix of T in this basis? How will you write it? So supposing BV is V1, V2, Vn, what is this? This is T V1, T Vn, each coordinates in basis BW. Okay, so all these things are coordinates in basis BW, right? So this is your matrix M of T BV BW, right? So this is the matrix. So given a basis for V and basis for W, you can come up with a matrix. So typically people take the standard basis for V here, standard basis for W, and give you a matrix A, right? So but for an arbitrary basis also, this is what you do. Okay, hope this is clear. Okay. So now what does SVD tell you? SVD tells you that there exists an orthonormal basis BV and an orthonormal basis BW such that M of T, BV, BW is diagonal. Okay, so it will be generally a square matrix, but a rectangular matrix, but that rectangular matrix will be diagonal. That's what this SVD tells you. Moreover, BV is basically the right singular vectors. BW can basically be the left singular vectors, a set of left singular vectors. BV is a set of right singular vectors. And this M of T, BV, BW not only is diagonal, but it has the singular values on the diagonal. Okay, so that's more interesting results about what the SVD says. Okay, so this is a restatement of SVD in terms of operators, and this is what we will prove. Okay, so we will prove this in the next few slides. Proof is going to be fairly involved. It's one of the longest proofs maybe we have had in this class. It just breaks up the ideas into smaller segments. None of the ideas themselves are complicated. It's just viewing them from the right point of view and carefully tracking what happens. Okay, so let's get into the proof. Okay, so a crucial role is played by T star T and square root of T star T. Okay, so a very important lemma in the proof is the following. Okay, so I've always been commenting about how T and square root of T star T are sort of the same in some sense, right? So I keep saying that all the time, so they give you a sense of being the same. So we saw from the null space, range space and all that, a lot of them are similar. The null spaces are the same, range spaces are the same. So there's lots of similarity. Well, range space is not the, you know what I mean. So null space is the same. So it's got a lot of similarity, these two operators, right? T and square root of T star T. So here is this lemma, which again brings out one more very interesting result, right? The norm of TV equals norm of square root T star TV. Okay, so when you hit both T and the square root T star T with the V, remember this TV. Okay, so it's important to remember this TV actually belongs to W and this guy belongs to V, right? So these two belong in two different vector spaces, but their norms are the same. Okay, and you can sort of quickly see that the proof is not very difficult at all. This is a very easy proof. It's just any algebraic manipulation proof is very easy, isn't it? So you just bring this to this side, T star T, write it as square root. And how did I do this? What is the final step? Reason for the final step? This is because, how did this happen? This is because square root T star T is self-adjoint, right? Since it's self-adjoint, if you push it to this side, you get the same operator. So the norms are the same. Okay, so this is a proof that these two are equal. Okay, so this is very important. The fact that TV and square root T star TV have the same norm. This will play a crucial role in SVD and its proof. Okay, so let's take the range of T, which is the set of all TV for V in V, right? This is the range of T, and range of T we know is a subset of, again don't forget, this is a subspace of W, right? And what about range of square root T star T? This is again set of all square root T star TV for V in V, and this is a subspace of V, isn't it? So this is a subspace of V, and both of these we know have the same dimension, right? So that's one of the results we saw in the previous lecture. These two have the same dimension, and now we have seen that TV and square root T star TV have the same norm, etc. And so it turns out one can define this very interesting interesting map S from range of square root of T star T from this set to this set, range of T. How will I define this interesting little map S? I will simply take square root of T star TV and map it to TV, right? Remember once again, every element of range of square root T star T is of this form, square root T star TV for some V. As you keep changing V, this thing will presumably change, okay? Same thing happens here. As you keep changing V, this TV also changes. I will take the square root of T star TV and map it to TV. Okay, so remember square root of T star TV belongs to V. I mean it's in that vector space. TV belongs to W. It's in the other vector space. So this is a mapping that I'm going to do. S goes from range root T star T to range T. Okay. Now this S has so many, very many interesting properties. I'm going to just put down all those properties and then maybe draw some other pictures to describe what's going on. Okay, so notice what's going on here. So you have V and you have W, you have range T. So, this takes you to T takes you from here to the range, and then you have how will square root T star work? Okay. So, it will have some other thing here. This was going to be range square root T star T. Okay, it takes you from V to V, right? So, it goes from V to V. Maybe I should write it like that, square root T star T, and that will be the range, right? It will go to this, from V it will go directly to that. Okay, so this is the sort of picture. If you want, in case you like pictures, you can keep that in mind. And what is this mapping? So, if you have a V here, V went to something like this under T, right? So, this would be TV, and this V would go to, this V would go to some place here under square root T star T, right. So, this point here would be square root T star T, V. And what is S going to do? S is going to take this guy to this. Okay, so this is that picture. Okay, hopefully this picture is clear to you. Okay, so you have V and W. T is a mapping that takes you from V to range of T inside W. Square root T star T is a mapping that takes you from V to range of square root T star T, which is inside V. Now, if you take a particular vector V, T will take you inside range T, square root T star T will take you inside range, the corresponding range there. This S is basically a map that maps this guy to that guy, okay, after the multiplication. Okay, so this is a picture. If you want, you can keep in mind. So, the first thing is S is well defined. Okay, if you have two different V's, V1 and V2, that went to the same point, okay, then they will go to the same point under T also. Okay, so this is something you can show. So, it is not very difficult. So, this implies square root T star T V1 minus V2 is 0, which implies V1 minus V2 is a null square root T star T, which is equal to null T, and that implies this guy, right. So, these two are equal, the null T and null square root T star T are the same. So, null of T, V1 minus V2 belongs to null of T. So, T of V1 minus V2 is 0, T V1 equals T V2. So, this map is well defined. Okay. So, if you have two different vectors going to the same point under square root T star T, they also go to the same point under T. Okay. So, it is well defined. Okay. So, this also shows you this kind of a manipulation. Okay, S is linear is not too bad to see. The other thing you can quite quickly see is that S is 1 to 1 and it is also onto. Okay. So, it is sort of like a 1 to 1 and onto map. It is injective, surjective. It's almost like an isomorphism in some sense, right. So, between these two things. So, that's what S is. These are easy to prove. I'm not going to go into great detail here, but this you can hopefully see why this is true. The dimensions are also the same, no. So, the range of square root T star T and range of T have the same dimension. So, this is also easy to see. Okay. So, from the lemma, so this is just by lemma. Okay. From that lemma, you can see this result, right. So, if you have a U which belongs to range of square root T star T and that U by S goes to some point here in range of T, that U and SU have the same norm, right. So, that is the restatement of this result, right, of the same lemma. U and SU have the same norm. Okay. S is linear, U and SU have the same norm. Now, that is very interesting, isn't it. So, when you have something that is linear and having the same norm, we know that this S will also preserve inner products. Okay. So, why? Because norms come from inner products or inner products come from norm. Both of these are true. As long as S is linear, you know that only summation U1 plus U2, U1 minus U2 S times that will show up in the norm definition. So, the inner products will also be the same. So, this is sort of how we showed for isometries, when they preserve norms, they also preserve inner products, right. So, this S is like an isometry from range of square root T star T to range T. So, it will also preserve inner product. Okay. So, I am not going to prove this result, I will just write something inner product can be computed from norms. Okay, I will leave it like that. So, this proof is easy enough to do. We have seen it in one other case. For the isometry case, we have seen this, the same idea you can use to show that this map S preserves the inner product. This is very, very crucial. So, notice all that we have done here. We have taken square root t star t, and then we have taken t, and we now have almost an isometry with what, I mean, we do not quite define it as an isometry. Isometry is between one vector space to itself. This is like from a subspace to another subspace. We have a map which is linear, it preserves norms, it preserves inner products. Okay. So, this is very crucial. So, once you have this, we can do something very interesting with it, and the proof of the SVD will follow. Okay. So, this is important. A few ideas, but the crucial idea is that the square root t star t and t are very similar in some sense, right. So, and that's what this is establishing clearly. Okay, so let's continue with the proof. We've done most of the hard work. Now it's just a question of carefully arranging everything and it will work out. Okay. So now square root t star t is also self-adjoint. Okay, of course t star t is also self-adjoint, and both of them will have a nice common orthonormal eigenvector basis, right. So I will take that as E1 to En. Okay. The corresponding eigenvalues will be the singular values of t, right, square root of t star t. If you take the eigenvalues of square root of t star t, they will be the singular values of t. I will write them as sigma 1 to sigma n. Now let us suppose this k is the rank of square root of t star t. It need not be full rank, isn't it? It can have some lower rank. So let us say k is the rank. So when k is the rank, remember it is a self-adjoint matrix. So sigma 1 to sigma k will be non-zero, and after that you will have 0. Right? So it will be exactly k non-zero eigenvalues, and after that it will be all 0. Okay? So that is how for rank and the eigenvalues are connected. So this is how it will be. Okay, so this is first step. This setup is easy to do. Now we will move on to the connection between range of square root t star t and E1, E2, En. Okay, so remember E1 through Ek are eigenvectors of square root t star t, right. So what will happen? So maybe I should write this out. Square root t star t times E1, for instance, is sigma 1 times E1. Okay. So this clearly belongs to range of square root t star t. Okay. So E1 also belongs to the range of square root t star t. That is quite easy to see. And this will be true all the way till Ek, right. The same thing is true. Oh, so I got it wrong the other way. T star t, Ek is sigma k Ek. And so this also will belong to range of t. This also will belong to range of t. So you have k as the rank of square root t star t. And here you have k orthogonal vectors. Okay. So remember if I took E1 to Ek, E1 to Ek will be an orthonormal basis of range square root t star t. Once I multiply by square root t star t, I will only get an orthogonal basis, because the reason is the norm of these guys, I will write down that in the next step, you will see the norm of each of these guys is actually slightly different from 1. I mean, so maybe I should show it to you. So you see that the norm of each of these guys, norm of square root t star t E1 is basically sigma 1. It's not 1. Okay, so you can't say orthonormal. It's orthogonal basis of t star t. So now I do this S map, right? So notice what I've done here. I've done the S map. What will happen to Te1,Tek, right? So this will also become an orthonormal basis of range T. Why is that? This is by property 4. What is property 4? The inner products are preserved by S. Okay. So when you have this set being orthogonal in range square root t star t, this set Te1 toTek will be orthogonal in range T, because this S map that we are doing from going from square root t star t E1 to Te1 preserves norms, preserves inner products. Since it preserves norm, the norm of Te1 and the norm of square root t star Tei, right, both of them have to be equal to sigma I. Okay. So they will all be sigma, the norms will be the same, and they will be sigma I, and they will also be orthogonal. Okay. So this is the crucial idea. Okay. So you have an orthonormal basis for the entire vector space V. Some of those vectors form an orthonormal basis for the range square root t star. You simply scale them suitably to get to the square root t star t form. This is scaled by sigma 1 or something, and then you use the S, you go to range T from range of square root t star t. Okay. So that is very crucial. So you get an orthonormal basis, you go to orthogonal basis, you apply S, you go to orthogonal basis of range T. Okay. So now how do I get an orthonormal basis from the orthogonal basis? You simply divide by the norm, and the norm is sigma 1, etc. So you divide. Okay, and you call this as F1 to Fk. Okay, notice how I've gotten this F. You got an orthonormal basis for the original vector space V. You assumed a certain rank, you went to the orthogonal basis for range of square root T star T, and then you did the S map, went from square root T star T EI to T EI, and you realize that will also be an orthogonal basis for the range T. Then you can divide by the magnitude you have, right, magnitude of these guys that you have by the, again by that lemma. So you get this wonderful result. You have an orthonormal basis for the range of T, which is simply a mapping of E1 to Ek under T. Okay, so that's the nice idea. This you can call as F1 to Fk, and once you do that, you can extend this F1 by F gamma Fk to an orthonormal basis for the entire W. Find the orthonormal basis for range T in this fashion, and then you extend it to all of W, and this will give you all that you want, right. So in this basis, if you pick the basis E1 and the basis F, you see that TEI, okay, so why is this diagonal? TEI, TE1 is sigma 1 F1, TE2 is sigma 2 F2, right, TEK is sigma k Fk. What is TEK plus 1? All of them are 0, right. Okay, why is that? Square root T star T Ek plus 1 not 0, so this T will also be 0. Okay, so this tells you that if you form a matrix for this basis, right, T will be diagonal with respect to this basis, you have to write down T1, T Ek, I'll put here, then TEN. Okay, how do you express this? This has to be expressed in the basis, in basis F1 to Fn, Fm, and you see TE1 is just sigma 1 F1, so it will be just sigma 1 here, sigma 2 here, so on till sigma k here. So it will be diagonal, everything else will be 0. So T becomes diagonal with respect to this basis, and the singular values show up exactly on the diagonal. So this relationship is crucial. TE1 is sigma 1 F1. So that's the crucial relationship that you have, that we have proved. Okay. So the last part we have to show is that this F's should also be left singular vectors for T, right? How do you show that they are left singular vectors? You just show T star. If you multiply T star by Fi, you will get, Fi is simply 1 by sigma I TEI. Okay, so you plug that in, you multiply, you get T star TEI. What is T star TEI? Sigma I squared EI, right? So it's an eigenvector for T star T, right? And then you get sigma I squared Fi. Right, so this T will come in, 1 by sigma I TEI is Fi, so sigma I squared times Fi. So T star Fi is sigma I square Fi. So Fi's are left singular vectors for T. Okay, so that's the idea. So what has happened overall is, if you want a picture, okay, so you have V, and we have W here. There is an orthonormal basis E1, Ek plus 1, En. These guys are inside range of square root T star T. Okay. What happens when E is applied to these guys? You have range T here. When T is applied to these guys, this goes to F1 all the way till this going to Fk, okay, and then all these other fellows under T go to 0, right. So the 0 will also be here, they all go to 0, okay. So this F1 to Fk ends up being an orthonormal basis. That was my property of that nice little relationship, that map S, which was like an isometry from range of square root T star T to range of T, and then you extend this guy to Fm. Okay, you extend this. So now you have an orthonormal basis, which gives you a diagonal for T. That's the idea. Okay, so it's a crucial little, interesting little insight into how SVD works. Okay, so that's the end of the proof, and we have shown this existence of two orthonormal bases under which any linear map becomes diagonal. Okay. So, final observations about the SVD. Okay. So, the notation is like in the previous proof. The first observation is, given that you have the product of F1s, diagonal, E1s, E1 transpose, etc., you can write T equivalently as this product. Okay. So, this is same as when you had the spectral theorem for self-adjoint operators, we could write it in this form, right? F1 would be equal to E1, right? You would got E1, E1 transpose bar, etc. Now, instead of E1, you will have F1. It's the same 3 matrix product with diagonal in the middle, column, row, etc. So, this is that product. You can quickly show rank of T is the number of non-zero eigenvalues, non-zero singular values. Okay. Range of T is basically the orthonormal basis F1 through. Orthonormal basis for the range of T is this F1 to Fk. An orthonormal basis for null of T is Ek plus 1 to En. So, this SVD gives you all that you need to know about the linear map. Okay. So, in fact, most numerical computations, you give any numerical package a matrix, M cross N matrix, it will first compute the SVD, and all the other things it will compute based on that. In fact, you can project to the range, right? You find an orthonormal basis for range T, so that gives you the projection, right? Everything you want, you can compute using the SVD. Okay. So, and the SVD has wonderful numerical methods today for computation. So, it plays a very important role just in terms of numerical implementations and etc. And also several other applications. So many interesting applications for SVD. In the next lecture, we will see a couple of very interesting applications for SVD, and that will be the conclusion of the course. Okay. Thank you very much.